Do you remember how you learned how to read? When you've put two letters together making an intelligible sound? What about when you did your very first math addition? I actually remember being on my grandmother's lap when she showed me that 1 + 1 = 2. Artificial intelligence, or AI for short, attempts to mimic the way for how humans learn. But to truly understand what we currently call AI, we must first understand how is it that AI seems to learn. Do they have like a secret database that we don't know about, or some hidden memory? How does it work? How does it learn or remember things? You see, if we start peeling AI like an onion and shed all of its layers, we find a concept that, if we look closely, is really all too familiar for us as humans: the concept of neural networks. Now, neural networks mimic the structure and behavior of the human brain. For instance, a single human neuron is essentially a cell in the nervous system that receives and transmits electrical signals through synapses. In isolation, a human neuron can't really do much, but in conjunction with other neurons, they form what are known as functional areas and cortical layers. And together, billions and billions of these neurons, amongst many other things, allow us to learn. But for us to really understand how AI and neural networks really work, we need to peel one more layer and find the simplest form of neural network there is: the single neuron, also known as the perceptron. The perceptron, being the most basic form of artificial neuron, it has only one input and one output. Now, it can have more than one input, but for now, let's just focus on just this one. If you are new to this is probably already sounding quite complicated, right? So I guess to really start our journey from the very beginning of AI, we need to ask ourselves one question: what is a function? If you ask this question to a computer programmer or a mathematician, I am sure that they will see the question from a different perspective. But their answer should pretty much be the same. A function is a concept that receives inputs and provides outputs. But let's focus on the mathematical explanation. If I give an x input to a function, that function will return an output y. Let's imagine we have the following x inputs 1, 2, 3, 4, and we want to know what the output y is going to be. Well, if we say that f of x equals x, and y equals f of x, then we can say that y equals x. It's pretty simple, right? So we know that if x equals 1, 2, 3, and 4, y, the output, is also going to be 1, 2, 3, and 4. Because, well, y equals x. Similarly, if we say that f of x equals 2x, then we know that y equals 2 times x. Therefore, y equals 2, 4, 6, and 8, which is obviously the double. This is really simple, right? I mean, we teach this kind of stuff to kids and early teenagers. We know the outputs by running the inputs through our f of x function. This is, of course, assuming that we know what that function is. But what if we didn't have a function? What if all we had were the inputs and the outputs? I mean, sure, we could plot this data in any type of chart, but I would have no mechanism to reproduce future values. And this is exactly what a neural network is: a function, or to be more specific, a function approximator. It could very well be a supermassive function with billions of parameters, for sure, but it could also be a really simple function as well. Assuming that I know what the inputs and the outputs are, we could try and recreate this function approximation to allow us to predict future outputs for, well, future inputs. But how do we go from this concept of a function approximator to a full-blown AI? Like we said earlier, this single artificial neuron is called a perceptron. So we're going to give it a name, okay? Let's call it Zane. Zane, the baby perceptron. So it's time that we send Zane, the perceptron, to AI school. The very first thing we want Zane to learn is to predict the next number out of a sequence of numbers. So, for example, let's give it two lists. One for inputs, where the inputs are 1, 2, 3, 4, and 5, and a list of outputs. And the outputs are 3, 6, 9, 12, and 15. We want Zane to understand the relationship between them so that when we give them a new number like 6 or 7 or 1394, Zane can tell with confidence what the output is going to be. Now here's the interesting thing. Just from looking at this, as humans, we can immediately see that the output numbers are, well, the triple of the inputs. If I ask you what 6 is going to be, you can almost instinctively say that it's going to be 18. And we know this because we learned the relationship between these numbers in school. So now we can very easily recognize that pattern almost immediately just from looking at it. So we need to teach Zane to do the exact same thing. Let's begin by writing down what we know in our code editor. So let's enter the inputs and the outputs. Now, if we plot these numbers into a chart, we can see that they form a straight line. This is also known as linear regression. So if we would put a 6 in here, for example, just by looking at the line, we know that the corresponding value is 18. Since the neural network is a function approximator, we know that our outputs are equal to our inputs times something else. Looking at the chart, the distance between one input and the other is denoted by its slope. And a good representation for slope in maths is m. But we will use w, and you're going to see why in a minute. So we can say that the outputs equal w times the inputs. Or in other words, if outputs are y, inputs are x, and our slope is w, y equals wx. Now let's replace these with the values that we already know, or at least one set of them. So the outputs 2 equals w times my input, which is 1. So it seems that all that Zane has to do is learn the correct value for w, and he will be ready to start making predictions. We now have a mechanism that we can use to teach our artificial neuron to predict outputs from given inputs. Looking at the diagram of our perceptron, or Zane as we call it, we can see the inputs that are going in and the inputs that are coming out. However, we now also have a new parameter with the relationship with the inputs, and that's going to be the weight, which coincidentally is the only parameter that, at least so far, we can modify. And naturally, this is also the parameter that will allow our artificial neuron to learn. This process of calibrating the weight is called the training process. Okay, I think it's time for us to return to our code editor and apply the things that we just learned. We know that we need to update the weights, and we know the formula that will allow us to do that now. So let's write a function to make the predictions. We can give w a very small value to begin with, but know that there are many strategies for weight initialization, and we'll cover those in future videos as well. So don't forget to subscribe and like the video to keep up with more of the good stuff. Next, let's create a prediction list, or vector to be more complacent with the machine learning lingo, and calculate a prediction for all our inputs. Now let's print the results of these predictions and see what Zane came up with. And yeah, poor Zane is very far off. And it makes sense, right? Because it was more like a lucky guess. We need to define a way to grade these predictions. Now, since we have the expected outputs, also known as the targets, and we have the predictions, we can just simply subtract one from the other for every single prediction and store these results in a vector. Now, this vector is commonly known as the cost, the error, or the loss. I mean, it has like 3 different names, but they all mean the same thing. It's essentially just a mechanism to grade how well Zane is making predictions. A very high cost means an F, and a very low cost means an A. And a 0 cost would be an A+. Or in machine learning lingo again, a 100% accuracy. Now, think of this error vector like the right and wrong answers that you get in a school quiz. It's good to know which questions we missed and which ones we got right, but in the end, the most important thing is the average of these results, which make up the final grade. With our error, or our cost, the average of errors will give us a single or scalar value for the overall cost. So let's sum up all the errors and divide them by the total number of targets so that we can get the average. This mechanism to calculate the cost is also known as the mean absolute error. Okay, it seems that our cost is quite high, so we need to bring it down. But how can we bring this cost down? The grade is an indication that a student has learned or, well, memorized something really well. So in order for the cost to come down, our perceptron needs to show that it's learning. Since the only parameter we have control is the weight, we need to update its weight. We do this by taking a small fraction from the error and add it to the weight. This little fraction that we're taking is also known as the learning rate. Like in human learning, we want Zane to learn little by little. So we start with a small value like 0.1. But, this could be even smaller, like 0.001 or 0.001. Since we are only taking one small fraction at a time, we need to do this iteratively. And also in machine learning, this is known as an epoch. This is a process that Zane must repeat time and time again until it gets the correct value. Okay, it seems that we are now ready to run a full cycle. So let's print these weights and costs. And still not there. So let's adjust our epochs and see what happens. Brilliant. Our cost is now 0 and our weight is 3. Now this continuous cycle to minimize the cost and updating the weights is known as cost minimization. Now in real life we have two types of students. The students that pass the final exam by just memorizing all of the course content, and these guys usually they can't apply anything that they learn in a new situation. And then we have the students that learn the course content and they can apply this anywhere. The same thing applies to machine learning. So some neural networks do really well with the training data, but very badly with brand new test data. And this is known as overfitting. And then we have some other neural networks that do great in like both scenarios, in both training and with brand new data. So let's create some new test data, different from our original data, obviously, and see how well it performs. Let's calculate the predictions. That's a great result. I mean, or at least pretty good. It seems that Zane learned its stuff. Remember that we are using a very archaic cost function here, the mean absolute error, but it's still a good result, I would say. Also because what we're trying to do is very simple. However, I'm sure some of you have already spotted a problem that we have here, especially in our predict function. If we look at our original charts for the y equals wx function, our line only intersects the origin. No matter how much I change the values, the line can't move up or down. For example, if I change the target value by 20, the regression line will never be able to fit the data. And to solve this problem, we need to give our neuron a new skill or a new parameter, also known as the bias. This type of input also has a weight associated to it. But since the bias value is always 1, and 1 times the weight will equal the weight, we just call this value, well, the bias value. With the introduction of a bias, our new learning formula can now be updated to y equals wx plus b. And this is the full formula for any linear regression for single or multi-layer perceptron, which, like I said before, we're going to see in other videos. For those of you that are more math savvy, this formula will probably resemble another one, which is the line formula, which is y equals mx plus b. And if I apply a little bit of differential calculus to this formula, we can see that w, or 3 in this case, is also the derivative of this formula, which is denoted by the slope. Now we know that the bias will allow our regression line to better fit the data. And since we increased our input data by 20, we know that the bias should have the value 20. If we plot this in the chart, we can see that we no longer intersect the origin and we have a nice regression line cutting through our input values. Similarly, if we change our predict function to include a bias and we modify our test targets by increasing them by 20, we can see that the perceptron won't have a problem making good predictions, as you can see here. However, the bias is a parameter that, just like the weight, forms part of the training process and as such should be adjusted accordingly. That is, during the training loop. Hard-coding values is not really training our perceptron, and therefore nothing is really being learned. So let's change that. Let's modify the bias, and just like we did with the weight, let's multiply our learning rate by our cost average. We will also update our print function so we can see what's happening inside of Zane's head. I'm joking, okay? I know that Zane isn't real. Or is she? We can run the code. But this doesn't really seem right. The bias already surpassed the value of 20 and the way is far from 3. Something's not right. What's happening is that we're treating both parameters equally, as if they impacted the function and therefore the neuron in the exact same manner. But that's not true, right? The weight, as we've seen, is the derivative of the function and therefore impacts the slope. And the bias, as we've seen, impacts the intersection of the line. Calculating their respective updates equally just won't cut it. What we need is to calculate how each of these parameters impacts the overall function and consequently the neuron. Welcome to the world of gradient descent and backpropagation. Now, I'm going to show you two versions to do this, for this particular example at least. The hard way and the easy way. As the good Portuguese that I am, let's start with the hard way. In order to update the weights and bias successfully, we need to calculate how each weight and bias impacts the function respectively. Now, I thought long and hard in how I could explain this to you with just code, but unfortunately, I really can't. I need to use differential calculus, and I promise I'm going to go easy. In calculus, the derivative of a function allows us to calculate the rate of change. More specifically, it shows how much the function's output changes when the parameters change slightly. In neural networks, this rate of change is also known as the gradient, or simply the vector of partial derivatives in respect to its parameters. I'll show you what I mean. Remember how we graded our Perceptron's predictions? By calculating the loss, and we used the mean absolute error function to do so. So to calculate the gradient vector that I just described, we need to show how the weight and the bias affect that score. And the result from that will form the gradient vector. In other words, in order to update the weight, we need the derivative of the cost function in respect to the weight. And in order to update the bias, we need the derivative of the cost function in respect to the bias. These derivatives form the gradient vector. Now, let's start with the gradient for the weight. To calculate the derivative of the cost with respect to the weight, we can't just do it directly. Why? Well, because if you look at the mean absolute error formula, or the MEI formula, there is no W in the formula. The W is embedded inside the formula for the predictions bit, which is Wx plus b. Therefore, we need to dive into the functions and use a concept called the chain rule of calculus. To solve the derivative of the cost with respect to the weight, we need the following steps. For instance, the derivative of the cost with respect to the weight equals the derivative of the cost with respect to the function, which is where W is, times the derivative of the function with respect to W. So this is how we break it down, because one function is chained inside the other function, hence the chain rule. If we put this together, these f functions here, they cancel each other out, and we get the derivative of the cost with respect to the weight. The derivative of the cost function in respect to f is sine targets minus predictions, and it is 1 if the target minus the prediction is greater than 0, minus 1 if the target minus the prediction is lesser than 0, and 0 if the targets minus the predictions equals 0. Let's write the f function, which is W times x plus b. The b we can just ignore because we are calculating this in respect to W, so it doesn't really matter. It's like a constant. And for W times x from the chain rule of calculus, the derivative of one term in respect to the other equals its opposite. For example, just a little side note here for maths. If we have f of x and y equals x times y, the derivative of that f in respect to x equals y, and the derivative of f in respect to y equals x. So it's the opposite, right? Therefore, in our case here, since we have f equals w times x, the derivative of f in respect to w is x. Like I said, once again, this is known mathematically as the chain rule of calculus. And it's one of the most important things to know in machine learning, neural networks, and well, science really. Never leave home without it. Time to go back to our code. We now know that to update the weight, instead of using the cost function, we need its derivative instead, with respect to the weights. Let's start with the cost derivative, which is sine costs equals, well, 1 if c is greater than 0, otherwise it's minus 1. And we're taking these values from our costs list. Finally, let's update the weight. W plus equals the learning rate times the average values of our cost derivative times the inputs, or x. Because as we've seen, it's with respect to the weight, so we need to multiply by the inputs. For the bias, it's pretty much the same process as the weights. We need to calculate the derivative of the cost with respect to the bias using the chain rule. But let me save you all the trouble. The bias doesn't really depend on the inputs, as it only moves the regression line up or down. So all we really need to do is the derivative of the cost function. But if you want to verify this with maths, I mean, by all means, go for it. Just calculate the derivative of the cost with respect to the bias, and you should end up with pretty much the same result. So for the bias, let's just simply multiply the learning rate by the average sum of the derivative of the cost function and keep adding it to the bias. Let's also change our cost average here so that we only get positive values, and also replace this targets with costs, just to make it a bit more obvious that it's the average we're trying to get. Now we need to calibrate our adjustment parameters, which, as we also learned, it's the epochs and the learning rate. Since we're working with gradients and we want small steps down the gradient mountain, let's start with a very small learning rate and a very large epoch. Also notice how the cost decreases, and therefore the accuracy increases as we increase the number of epochs. So it's working. Our little perceptron here is learning. Our cost is still very high, so let's keep increasing the epochs until we hit a sweet spot. And 6,000 epochs seem to do the trick. And that's it. Our Perceptron Zane can now make a full, simple linear regression. Now, do you remember I told you there was an easier way to solve this problem? Or at least for this particular use case? Let me show you guys something really cool. For this particular use case here, I didn't need to explicitly derive the cost function. I could just multiply the cost by the inputs, because the perceptron updates W and B in the direction that minimizes the error. So if we just revert to where we were, and we simply change this line for the weights and multiply the cost by the inputs without deriving it and keeping the same formula for the bias, this also works. Why is that? Well, this is known as gradient descent intuition, or direct error propagation, where the error directly influences the update of W and B based on the input X. But this is for simple stuff like this. Anything more complex and you would need to derive, just like we did earlier, which is why I started the harder way to do this, not for any other reason, okay? Not because I'm being really mean to you guys. All right, folks, this has been quite a ride, and I really hope that you guys have enjoyed it so far. For the last part around gradient descent and the beginning of backpropagation, don't be too discouraged if you didn't fully understand it, okay? I am making some more videos on the series, and I am sure that with time it will start making more sense. Believe it or not, I actually shot this final part 3 times. I mean, as you can see, there's light coming from the outside already. It's a concept that is hard to understand and, believe me, hard to explain. Our Perceptron Zane is now able to perform very simple linear regressions. But what happens when the data isn't linear, or when we have more than one input with real data? How do we go from here to make Zane write a beautiful poem in the style of Homer? I would like to invite you guys and girls to continue on this journey with me, our trip from the origins of AI. So subscribe and like the video, and I will see you guys soon, all right? Take care and bye.